In Interchapter A, we're going to be talking about nomenclature and the basic system for naming organic compounds. In this first group of slides, we're going to focus on alkanes. For nomenclature, we're going to be looking at the rules on how to name structures. That's what nomenclature means. The rules that we're going to be following are the IUPAC rules, the International Union of Pure and Applied Chemistry. So basically, they have defined the rules and we all follow them so that we all name our compounds the same and know what chemicals we're talking about in journals or in different papers. My recommendation for you as we go through all of our nomenclature chapters is to have a notebook or a binder set aside or an area in your notebook set aside for just nomenclature, because we'll continue to add on to all of these rules as we progress throughout the semester. And it makes it a little bit easier if all the rules are grouped together as you start naming more and more complex compounds. So all of our compounds under IUPAC nomenclature will have a locant, a prefix, a parent, and a suffix. So with this, the locant tells us a little bit about where the substituents and the functional groups are. So the key with the locant is the where. It's going to define where within the molecule we find the substituents or we find the functionality. The prefix is really going to define what the substituents are. So what branches or what groups are on our molecule itself. The parent is going to define the number of carbon atoms that we have in the longest chain, or what we call the parent chain, the main chain associated with our compound. The suffix is then going to describe for us the functionality. So it's going to be determined by the different types of functionality that we're going to see within our structure. So as we get ready to add on nomenclature rules, it's going to focus on all these different pieces and parts, the parent, the suffix, the prefix, and the locant, and how we put all that information together to tell us and describe the structure or the molecule for us. So our focus is going to be on alkanes. Remember, alkanes contain only CC single bonds and CH bonds as well. So that's going to be our main focus. It's going to be on our alkanes. We're going to focus first on our straight chain alkanes. These would be our linear alkanes. For our linear alkanes, they're going to have the general formula of CnH2n plus 2. When we talk about our straight chain alkanes, the ending that we are going to use, which is the functionality, the ending, that suffix that we're going to be using is going to be ane, A-N-E. The parent that tells us the number of carbon atoms that we're going to have is going to be here in front. And what you really want to start memorizing for me is that parent prefix that we have, which for this case would be meth. And that meth would imply that we have one carbon atom. So this is another one of those times I'm going to say flashcards are going to be the best way to do this. To memorize that meth means one carbon atom. So if we're looking at our straight chain formula for methane, our formula for methane would be CH4, and it would just be one carbon atom. So there would be no line structure that we'd be looking at. So for the next one, we have ethane. So the prefix of F is what means that we have two carbon atoms. So our formula would be C2H6, and it would just be the two carbon atoms connected together. If we look at propane, prop is our prefix for 3 carbon atoms. Our formula would be C3H8, and our line structure would have our 3 carbon atoms. If we talk about butane, but represents 4 carbon atoms, so our formula here would be C4H10, and we would have our line structure with 4 carbon atoms. Pentane, pent is what means 5 carbon atoms, so this would be C5H12, and we would have 5 carbon atoms in our line structure. Hexane, the prefix of hex means 6 carbon atoms, so this would be C6H14, and we would have 6 carbon atoms in our line structure. The prefix of hept in heptane means 7 carbon atoms, so this would be C7H16, and we would have 7 carbons in our line structure. For octane, oct tells us that we have 8 carbon atoms, so this would be C8H18, and we would have our 8 carbon atoms. For nonane, non means 9, so this would be our C9H20, and we would have 9 carbon atoms in our chain. Decane, dec would tell us that we have 10 carbon atoms, so this would be C10H22, and we would have 10 carbon atoms in our chain. Undecane, undec would tell us that we have 11 carbon atoms, so this would be C11H24, and we would have 11 carbons in our chain. Dodec would be 12, and this is the last one that you need to recognize for me is the 12 with the dodec, and this would be C12H26, and we would have a 12 atom carbon chain. So again, you want to be memorizing not only methane, but what that initial prefix of meth tells you how many carbon atoms. So a couple different things that you want to be learning here. That ane ending that we put on any of these just tells us that we have all single bonds between the carbons and the hydrogen. So it's our alkanes. With our alkanes, we can also look at them in terms of cyclic alkanes or cycloalkanes. These are going to be our cyclic compounds, so they're going to come in a ring for us. The general formula for cycloalkanes is going to be CnH2n. You'll notice that we're going to lose 2 hydrogens because we have to now connect all of our carbons in a cycle, in a chain together. The prefix that we're going to be using is going to be the prefix of cyclo in our name. So if we have 3 carbon atoms, it becomes cyclopropane. So you'll notice prop for 3 carbon atoms, cyclo telling us that they are all in a ring together. And ane tells us that they are all single bonds. So our formula here would be C3H6. And our line structure would look like a triangle. We have 3 carbon atoms all connected in a ring. We have cyclobutane, which means we have 4 carbon atoms, so this would be C4H8. And all 4 of those carbon atoms would again be connected in a ring for us. Cyclopentane would be C5H10. And we would have all 5 of our carbon atoms connected in a ring. Cyclohexane is 6 carbon atoms in a ring, so this would be C6H12. Cycloheptane would be 7 carbon atoms, so we have C7H14. This is the one that you want to be very, very careful on drawing. It is one of the hardest ones to draw, but you do need to make sure that you can draw all of these rings for me. We can then also have cyclooctane, C8H16, and this would be when we would have 8 of our carbon atoms connected in a chain as well. We can have larger rings than this, so you want to be able to draw any of them. These are some of the most common ones that we will draw, but they are by all means not the only ones that you'll be expected to draw this term. So not all of our molecules are these nice straight chain linear compounds. Oftentimes they are very branched. We looked at some branch structures earlier when we were talking about physical properties. So we do need to talk about how we're going to start naming and start looking at those branched groups. Those branches coming off are what we're going to refer to as substituents. When they are carbon chains, we refer to them as being alkyl groups, carbon chains, branches coming off of that main carbon chain that we have. Basically what an alkyl group is, it's an alkane chain that is missing 1 hydrogen atom. And we're going to name it as such. We're going to name it as an alkane chain that is connected to the parent chain. So the way that we're going to name it is we're going to replace that ane ending with the il ending, the YL ending. So if we have something like methane, we looked at methane previously. It was our carbon atom that had 4 hydrogens associated with it. That is methane. If I want this to become a branch, we would refer to it as the methyl branch. So we're going to remove one of those hydrogens, it does not matter which one, and we're going to connect it to our main branch. So the way that I'm going to start drawing these is when you see that squiggly line across the bond, it means that there's another carbon parent chain there in some form or fashion. So this is a substituent coming off. This one carbon atom is connected to a whole bunch of other carbon atoms that is a longer chain than what it is. So that's what we mean by an alkyl group or a branch or a substituent. We're going to use some common abbreviations, some parentheses. Instead of drawing out the CH3, oftentimes you might just see an ME listed. And that ME just stands for this methyl group, this CH3 group, instead of actually drawing out the carbons and the hydrogens. We can also then have ethane. So ethane, remember, was our 2-carbon chain. So there's our Lewis structure for ethane. For the ethyl branch, what we are going to do is we are just going to remove one of the hydrogen atoms and connect it to our chain that way. Again, it really doesn't matter what hydrogen we remove, we're just going to be removing one of them. So propane was our 3-carbon chain. With our propane to go into propyl, again, we're just going to be removing one of those hydrogen atoms. So getting into that line structure, this is what our line structure would start looking like. We have a 3-carbon branch coming off of another very long chain. Ethyl's abbreviation is typically ET. You'll see propyl abbreviated with a PR. We can also have a butyl branch. A butyl branch comes from our butane, which is 4 carbon atoms. So it would be a 4-carbon branch coming off of a longer branch or a longer chain. We may also see some pentyl branches. Pentyl will be 5. So we would have a 5-carbon chain coming off of our main chain or large chain. We will also see those cyclic rings as branches as well. So we can have a cyclopropyl group. So for our cyclopropyl group, we would have that 3-membered ring coming off of a chain. We can also talk about our cyclobutyl groups, where we would have that 4-carbon cycle coming off of our parent chain. We will have cyclopentyl groups as well. So a 5-membered ring coming off of our parent chain. And we can also have cyclohexyl groups, which would be that 6-membered ring coming off of our parent chain. So what you want to notice with all of these is just kind of how we have changed that ending. We have taken the ane ending and we have made it a ill ending on all of these. So we still need to know what that prefix tells us in the terms of the number of carbon atoms that we have. And then that is just now going to be a group connected to a very long carbon chain. So now let's put all of this together in the context of actually naming a compound. So here's a structure that is drawn for you and we want to be able to put some nomenclature to it, give you an actual name for this organic structure. So the first thing we have to do is we have to find the longest carbon chain. This is that parent chain or the parent that's going to be used in our nomenclature. You're going to find the longest carbon chain by literally connecting all the carbons together without picking up your pencil. To be the longest possible carbons that we can connect together without backtracking or without picking up your pencil. If 2 chains are the same length, so sometimes you'll be able to go multiple different directions along your chain. If you have 2 chains that are the same length, you are going to use the chain with the most branches as being the parent chain. So if one directionality only has 1 branch, the other way that still has the same number of carbon atoms has 3 branches, we're going to choose the path that has 3 branches. If there is a ring, and if the ring is equal to or larger than the straight chain, the parent becomes the cycloalkane, and we would name it as a cycloalkane that has branches on it. If the ring is fewer than a straight chain, so if that ring is smaller than the number of carbons in the chain, we name the ring as a cycloalkyl substituent. So the ring becomes the substituent, and the chain becomes the parent. So you really need to make sure that you are counting appropriately. So what we need to do with our example is we do need to find the longest carbon chain, recognizing that the longest carbon chain does not necessarily need to be a straight line. So if I follow along, I have 2 options for my counting. We always have to start at the end. So I can go 1, 2, 3, 4, 5. So I could say that my purple is equal to 5. We can then go another directionality. I could still start here and go 1, 2, 3, 4, 5, 6. And we can say that that yellow chain is equal to 6. So it's really the yellow chain that becomes my longest parent chain. So I'm just going to go through and I'm going to highlight that as that is my longest parent chain. So there's my chain. It is 6 carbons long, and I have one branch coming off of that chain. So it is your job to find the longest carbon chain. The next step is going to be to number all the carbons in that parent chain so that the first substituent is on the lowest number. So your job is to now number the carbon chain so that the first substituent is on the lowest number. If the first substituent is the same number in both directions, so you notice there are 2 ends to our chain, if we go in either direction and we get to the same first substituent, so they both end up on carbon number 2, you then use the second substituent and you want to make that the lowest number. And then the third substituent and make that the lowest number. So the goal is to have as many of them on the lowest number as possible. But this is if and only if the first substituent is on the same number in both directions. Your job is to first make the very first substituent on the lowest number possible. If we have a ring, and if we go in both directions, we have the same numbering notation, then we will use alphabetical order to prioritize, meaning we will put the one that comes first in the alphabet on the lowest number substituent. So that is what we'll do with rings when it really doesn't matter which direction you go in terms of numbering because there is no end. Your job is then to use the alphabet to prioritize. And the one that has the highest comes first in the alphabet will have the lowest number. So let's look back at our structure where we already have our parent chain highlighted here in yellow. So just kind of redrawing it to clean it up a little bit. Our job is now going to be to number it. So I can start on either end and I can go 1, 2, 3, 4, 5, 6. Or if we number something else in green, I number going the other direction. So 1, 2, 3, 4, 5, and 6. So now my job is to look at the branch. In the red, the branch is on the 3. In the green, the branch is on the 4. So my red numbering is correct in terms of the numbering that I would want to see. Because we want that branch to be on the lowest number possible. So I would number starting with the red line, starting with the 1 up top, and then I would number along all 6 of my carbons in the parent chain. The next step is going to be then to identify and number all the substituents. And this is really where we're going to be using our locant. You may have more than one substituent per carbon atom, and that is okay. We would just be using that locant multiple different places. So if we actually look at this, the branch that I have here, we've already said this is on 1, 2, 3, 4, 5, 6. The branch that I have coming off is only 1 carbon atom long. So this becomes a methyl branch. So that's where you have to know your prefix to go with your number of carbons. It's only 1 carbon atom, so it's a methyl branch. And it is on the 3rd carbon atom, so I'm going to put the locant in front of it. So it becomes locant, then substituent. So this becomes my 3-methyl branch. So from here, we're going to write our name, and we're going to write our name as one word. And the key here is it's one single word. There are no spaces in our organic nomenclature, unless I tell you a couple of exceptions. But for the most part, there are no spaces in our word. And I will tell you right now, SmartWorks is very, very picky. You have to have the correct format to get the answer correct, which means if you include any spaces, it will mark you wrong. We are going to write our name as one word. We will use hyphens to separate numbers and letters. So you'll notice I used a hyphen to separate the locant from the substituent name. So we'll use hyphens to separate letters and numbers. We will use commas to separate any numbers. So we will use commas to separate any numbers. We will put multiple substituents in alphabetical order. So if we have more than one branch, we will list them in alphabetical order. It does not matter number order. It does not matter what the locants are. Those locants do not have to be in numerical order. What we do is we alphabetize the substituents. So ethyl would come before methyl, irregardless of their locants. If we have multiple of the same substituent, so say I have multiple methyl groups on different carbon atoms or even on the same carbon atom, we're going to use Greek prefixes, di, tri, tetra, penta, etc. to tell you how many. So if I have 2 methyl groups, I'm going to say dimethyl. You do need a locant for each substituent. So if I have a dimethyl, I need to have 2 locants, meaning I need to have 2 numbers, even if they're on the same carbon atom. If I have a tetramethyl, I need to have 4 locants, 4 numbers in front of it to tell you where they are, even if they're on the same carbon atoms. We do not use those prefixes for alphabetizing. So if I have a dimethyl, I'm still going to alphabetize by the M, not the D. So we will not use those Greek prefixes in alphabetizing. They're just there to tell us how many. So let's take the compound that we just walked through and let's put it all together. It is easiest to look at organic nomenclature from right to left versus starting out and thinking about it from the locant to the end. So in my structure, I have a 6-carbon structure so that I know it is a hexane structure. It is all single and double bonds, so my parent becomes hexane. I know that I have a 3-methyl substituent associated with it. So putting all of that together, I'm going to write my name as 3-methyl hexane. There are no spaces between any of the letters. There is a hyphen between the number and the letter, so between the 3 and the methyl, between that locant and the substituent, but there are no spaces between anything else. So this would be 3-methyl hexane. So let's look at a few other examples. My encouragement to you right now is to pause the video and try to name the first 3 compounds. Try to draw the second compounds. Once you are done, come back and unpause the video and see if you have done things appropriately. So I would use this chance to practice and see if you understand the rules before listening to the final answers. So my encouragement is to pause the video now and come back later. So for our first one, the structure here would be called 2,2-dimethyl butane. We have a 4-carbon chain, so 1, 2, 3, 4, numbered to put the substituents on the lowest possible carbon number. They are both methyl groups. We have 2 of them, so dimethyl. They are both on the locant of 2, so please make sure you have included the 2 twice. You need to have as many locants as you do groups, so 2,2-dimethyl butane. Our second one is going to be 6-ethyl 2,2,4 trimethyl nonane. So our longest carbon chain here is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Along with that, we have numbered it so that the first substituent is on the lowest possible number. So my first substituents are on 2 versus going the other direction, which would put them on 4. We have then alphabetized. So notice ethyl comes before methyl, and it does not matter what the locants are. So we alphabetize. So ethyl comes before methyl. We alphabetize by the M, not the T for the trimethyl. And we include, once again, all of the locants for all of the substituents. Our third example is 1-ethyl 2-methyl cyclohexane. So with this one, we have a ring, so it does not matter which way we number. So we number based on the alphabet. So I'm going to put ethyl first and then methyl, so 1, 2, 3, 4, versus numbering 1-methyl 2-ethyl. So this is where they're both the lowest. They're both on substituents 1 and 2. So I'm going to prioritize by the alphabet. So ethyl comes before methyl, since it is a ring structure. So for 2,2,5-trimethyl 6-propyldecane, drawing is usually a little bit easier than naming because the structure is your own. This is where it's even easier to start at the right and move to the left. So I know it is a decane. Decane means 10, so I have 10 carbon atoms. And then I'm going to pick whichever side I want to number from. So I know on carbon atom number 2, I have a 2 methyl group, so 2, 2 with my methyl. I also have another group on carbon atom number 5. So there is my 2,2,5-trimethyl. On carbon atom number 6, I have a propyl group. So remember, propyl means 3, so I have a 3-carbon chain. So this would be my structure for 2,2,5-trimethyl 6-propyldecane. For the last one, we have a cyclohexane ring, so that is our 6-membered ring. From there, on carbon atom number 1, I have a methyl group, and it doesn't matter which carbon you make carbon atom number 1. It is wherever you feel like starting. And then on carbon atom number 3, I have a propyl group, which is again a 3-carbon chain. So again, it doesn't matter which direction you rotate around the ring. You could have gone to the left or to the right, but that relationship should be a 1 to 3 relationship. The more you practice with nomenclature, the easier this will become. So there are a lot of places to practice. You can even do a Google search on organic nomenclature practice, and it will pull up lots of documents. The more you practice, the easier naming becomes.